Welcome back to Bite-Sized Breakthroughs, the podcast exploring cutting-edge research in the world of AI. Today, we're diving into a fascinating paper that tackles a crucial challenge in deploying large language models: how to balance accuracy with efficiency. Joining me is Dr. Paige Turner, lead researcher on this paper, and Professor Wed Spectrum, a renowned expert in computational linguistics. Paige, let's start with the basics. What's the main problem addressed in this paper, and why is it so important?
Thanks, Alex. The paper dives into the trade-off between accuracy and efficiency when quantizing large language models, LLMs. Imagine LLMs like giant brain models that are trained on massive amounts of data, allowing them to perform impressive language tasks. But their sheer size, often containing billions of parameters, makes them computationally expensive to run, needing tons of memory and processing power. So, the key challenge is how to make these models smaller and faster without sacrificing their accuracy.
It sounds like a classic optimization problem. So how do you achieve this compression?
That's where quantization comes in. Instead of using the usual 16-bit floating point numbers to represent each parameter in the model, we reduce the precision to a lower number of bits, like 4-bit or even 3-bit. This effectively shrinks the model's memory footprint and reduces the time needed for calculations. But of course, the question is, how much accuracy do we lose in the process?
That's a great explanation, Paige. Now, Professor Spectrum, from your perspective, why is understanding this trade-off so crucial for the future of NLP?
Alex, you're absolutely right. It's not just about making models smaller and faster. It's about making them accessible. The real impact lies in expanding the reach of NLP technologies to real-world applications and users. Imagine a world where powerful language models are deployed on mobile devices, in resource-constrained regions, or even on small, low-power embedded systems. This paper's findings could unlock a whole new wave of innovation.
That's a compelling vision. Paige, what were the key findings of your research?
Our main finding is that 4-bit precision is the sweet spot. It consistently maximizes zero-shot accuracy while minimizing the model's memory footprint across different LLM families and scales. We conducted over 35,000 experiments with various models, systematically varying the bit precision from 3 to 16 bits and evaluating their performance on zero-shot tasks and perplexity. This extensive analysis revealed that, across all these scenarios, 4-bit models consistently outperformed models with other bit precisions.
That's quite a strong statement. Could you elaborate on what you mean by zero-shot accuracy?
Sure. Imagine you have a language model that's been trained on a massive data set. Zero-shot accuracy measures how well this model performs on a new, unseen task without any prior fine-tuning or specific training for that particular task. It's like testing a student on an exam they've never prepared for. Essentially, we want to see if the model can generalize its knowledge to solve new problems.
That makes sense. So, you're not just looking at how well the model performs on tasks it was specifically trained for, but on completely new challenges. Professor Spectrum, does this approach have any limitations?
It's a very rigorous approach, Paige, but indeed there are limitations. The zero-shot evaluation focuses on a general understanding of language, but for specific tasks, fine-tuning might be necessary to achieve optimal performance. Also, the findings are based on specific LLM families and parameter scales. It's important to investigate how these results might generalize to other types of models and architectures.
Valid points. Paige, did you explore any techniques to further improve scaling at specific bit precisions?
We did. We discovered that, beyond bit precision, certain quantization methods play a crucial role. For instance, we found that smaller block sizes and specific data types like quantile quantization and floating point representation can significantly enhance scaling trends, especially for 4-bit models. Imagine splitting the model's parameters into smaller blocks and quantizing each block independently. This helps to minimize the impact of outliers, those rare extreme values that can distort the quantization process.
So we're not just looking at the bit precision of the model, but also how we structure and manipulate those bits to maximize performance. Could you explain quantile quantization and floating point representation in more detail?
Sure, let's start with quantile quantization. Imagine you have a set of values you want to represent with a limited number of bits. Quantile quantization ensures that each bit pattern represents an equal number of values, like distributing a set of students into classes with an equal number of students in each class. This is an information theoretically optimal approach, maximizing the efficiency of each bit used. Floating point representation, on the other hand, allows for representing numbers with a wider range and potentially higher precision using a combination of exponent and fraction bits.
This is really interesting, Paige. It's fascinating how even the way you organize and structure the bits can impact the overall accuracy of the model. Professor Spectrum, do you see any potential challenges in implementing these methods?
Absolutely, Alex. While quantile quantization is theoretically optimal, it involves using lookup tables, which can introduce complexity and potential performance bottlenecks when deployed on hardware. This is where hardware design needs to catch up. We need to develop hardware architectures that can efficiently handle these specialized data types.
That's an important point. So while the paper provides valuable insights into the theoretical and practical aspects of quantization, it also highlights the need for future research and collaboration with hardware engineers.
Indeed. We also explored outlier-dependent quantization, where we treat certain outlier features with higher precision. However, while it improved stability at 3-bit precision, it didn't offer any scaling benefits for 4-bit models, further reinforcing the case for 4-bit precision as the optimal choice.
It seems like the paper also touches on the potential of one-shot quantization methods, right?
Yes, Alex. While our research focused on zero-shot methods, we did highlight the potential of one-shot methods like GPTQ. These methods, while potentially more accurate at low-bit precisions, require a mini batch of data for optimization and can be computationally expensive. However, our findings on the importance of factors like block sizes and data types seem to translate to one-shot methods as well, paving the way for future research combining these approaches.
This is fantastic, Paige. Your work provides a very clear roadmap for future research. But before we get into that, let's recap the key takeaway. So essentially, 4-bit quantization is the optimal choice for balancing accuracy and efficiency, with data types like quantile quantization and floating point representation further enhancing performance, and smaller block sizes helping to mitigate the impact of outliers. Am I summarizing this correctly?
You've got it, Alex. 4-bit precision, when combined with these techniques, allows us to significantly shrink the memory footprint and accelerate inference, opening up exciting possibilities for deploying LLMs in resource-constrained environments and pushing the boundaries of NLP applications.
Professor Spectrum, from your perspective, what are the broader implications of this research for the future of NLP?
This paper could be a game changer. Imagine deploying LLMs on mobile devices, bringing the power of language processing to everyday users. This research opens up avenues for developing more efficient and accessible NLP technologies, potentially impacting fields like education, healthcare, and customer service. We could see personalized language learning experiences, improved patient-doctor communication, and more natural and intuitive interactions with AI-powered systems.
It's truly exciting to think about the potential applications. Paige, what are the next steps in this research?
We're now focused on further exploring low-bit precisions below 4-bit, investigating how to improve scaling trends for these precisions. We're also looking at developing new data types that are both bit-level scaling efficient and hardware efficient, addressing the limitations of current approaches. Another exciting direction is to develop methods that effectively preserve outlier information without sacrificing scaling efficiency.
This research truly pushes the boundaries of what's possible with LLMs. Thanks to both of you for sharing these insights. This has been a truly illuminating conversation. Paige and Professor Spectrum, thank you for joining us on Bite-Sized Breakthroughs.